Welcome back to our electrochemistry. So in the last part 1 of our electrochemistry, we were discussed about electrochemical cells and galvanic cells, Nernst equation, as well as EMF of the cell. So we have calculated so many numericals on those galvanic cell notations, as well as Nernst equation, and all of them we have practiced. We have tried to cover maximum part of that. So we are in the second part 2 of our electrochemistry. So where we will be discussing on the conductance of electrolytic solutions, the conductance of the electrolytic solutions using KOHLRAUSCH law, very important. So again, electrolytic cells. So in that electrolytic cells, we are going to discuss the laws of electrolysis, that is called as Faraday's law. So both very important concepts. So we'll take up this concept today and we'll try to solve as many problems as possible. So with the main discussion will be on electrolytic cells as well as Faraday's laws, and conductance also will solve. A special discussion will be there on KOHLRAUSCH law. So what is this electrolytic solution? Electrolytic solution, conductance of the electrolytic. So that is our first part. So before we are going to solve all the numericals directly, so I am going to take 1 minute. I will revise you with some very important concepts of conductance. First, what do you mean by the conductance? Conductance is nothing but it is the ease with which a solid or maybe a liquid is going to conduct the electricity. So it is the ease with which our liquid or a solid is going to conduct the electricity. So is a measurement of conductance, how much it can easily allow the current to flow. The flowing of current, when it is flows from either a solid or liquid, so how much it is flowing, that can be known by the conductance. So conductance of solids, when we study the conductance of solids generally, so the conductance of solids will say, in solids the conductance is due to electrons. In solids our conductance is due to the movement of electrons, which we will call it as current. In solids the movement of electrons, flow of electrons, whichever you call. Whereas in solutions, especially electrolytic solutions, so what do you mean by this word electrolytic solution? Electrolyte is a substance which in its melt form or in the solution form is going to conduct the electricity. That is called as electrolytic solution. So a compound, if you take an example, very famous example of NaCl, so this is an electrolyte. If it is dissolved in water or if it is got melted, then you can call it as fused. It will form Na plus and Cl minus ion. That means an electrolyte will have cation as well as anion. When they are melted or they become solution, they will form ions, their corresponding ions, and these corresponding ions which are there present, those ions will conduct the electricity. So in solids the electrons are responsible for the conduction, whereas in solutions, especially electrolytic solutions, the movement of ions will give you the electricity. This is the basic difference between a solid as well as a electrolytic solution. Here the conductance is due to ions of the electrolytes. So the conductance is due to movement of ions. When it is due to the movement of the ions, you can see it here. Our sugar is not an electrolyte because it do not form ions when it is dissolved in water. Therefore, it won't conduct electricity. You cannot call sugar as an electrolyte, and this is not an electrolytic solution. If you can see NaCl is a very good electrolyte. It's a good electrolyte. When it is a very good electrolyte, when it is dissolved in water, you can see Na plus and Cl minus ions are formed. These movement of Na plus and Cl minus ions will lead to conductivity. Either you can take it as a solution, I said, or you can take it in a fused form, that means in a melted form also. But whereas in solid form, they won't give you electricity. This also must be remembered. And the conductance of the electrolytic solutions, they depend on so many factors like nature of the electrolyte, or size of the ion, or solvation of the ion, or the viscosity of the solvent, concentration of the electrolyte, as well as temperature. So these are the things we have to keep in mind. So these the conductance of these electrolytic solutions are measured by a special meter, the special device which is called as conductometer. This is a conductometer. You can see this is our conductometer, which is containing two platinum electrodes. They can take platinum electrodes, or they can take any other inert electrodes. We can consider any electrodes, but that meaning is you have to have two electrodes as well, which are connected to electricity. They are dipped in water. This is called as conductivity cell. So this conductivity cell is used to measure the conductance. So this conductance is given by the formula conductance is equal to 1 by resistance. Conductance is equal to 1 by resistance. G is equal to 1 by R, where G indicates the conductance. You need to remember the formulas, because formulas are very important in solving our problems. So conductance is equal to 1 by resistance. R, I can write resistance is equal to, resistance is nothing but resistance is equal to rho into L by A. If you remember, in the previous classes you might have studied, where rho is called as resistivity, L is the length between the electrodes. Whatever the length between these electrodes is called as L, and area of cross section in between these two electrodes, how much area of cross section is there, that is called as A. So I can write it as 1 by rho into L by A, or I can write it as A by L into rho, right? A by L into 1 by rho, A by L into 1 by rho. This 1 by rho, it is called as conductivity. What it is called as? Conductivity, which is shown by symbol kappa. This is called as kappa. So which is shown by symbol kappa, that is conductance is equal to A by L into kappa, correct? This is called as conductivity, or it is called as specific conductance, or it can be called as specific conductance. So when I write the formula for now, for conductivity, I can write conductivity is equal to conductance into L by A, correct? If I say this one here, this is called as specific conductance, or it is called as conductivity. That means conductivity is nothing but it is the conductance of the solution, where length between the two electrodes is taken as 1 and area of cross section is also 1. When L is equal to 1, length between the two electrodes is 1 and area of cross section between the two electrodes is also 1. The solution conductance is called as conductivity. So L is equal to 1, A is equal to 1 are the conditions. So this specific conduction, when on dilution, or you can say decrease in concentration, or you can say with increase in the volume of the solution, what will happen is the specific conductance decreases. The specific conductance decreases with the dilution, because the number of ions which are present in between these two electrodes will decrease when the conduction is decreasing. Conductance is decreasing. So what will happen? The number of ions which are present in between these two electrodes will decrease, because of the volume is increasing, or due to dilution they will move away from each other. The ions are away from each other. So we know that the conductivity is due to movement of ions. Then the ions are less, automatically the conductance also becomes less. So specific conduction decreases due to dilution. Then there is one more word to know about the conductance, which is called as molar conductance. Very important, very important. Molar conductance. Molar conductance is given by symbol lambda m. Molar conductance. Molar conductance means it is the conductance of the solution containing 1 mole of the electrolyte. If the solution that you have taken here, you have taken glucose, not, you should not take glucose, which is not an electrolyte. So any electrolyte like NaCl or KCl, HCl, any electrolytic solutions when you take, if the concentration of our electrolyte is 1 molar, then the conductance is called as molar conductance. Whereas this molar conductance will increase with dilution. The molar conductance will increases with the dilution. Why? Because if you write the formula for the molar conductance, the molar conductance, I can write it as molar conductance into is equal to specific conductance into volume. Molar conductance is equal to specific conductance into volume. So this is called as molar conductance. So when the volume is increasing, automatically molar conductance also increases. So the formula that we should use to calculate the molar conductance is lambda in m is equal to 1000 into kappa by C, where C is called as concentration. This is the equation that we will use to solve the problems. So lambda m is equal to 1000 into kappa by C. You should remember where K is called as, kappa is called as specific conductance and C is called as the concentration of the electrolytic solution, the concentration of electrolyte, right? So very important formula. After that, a scientist called as KOHLRAUSCH, which is very important law for us. A scientist called as KOHLRAUSCH, he has found out that so the conductivity of the electrolytic solutions, especially any solution, especially for strong electrolytes, he has done. So the conductivity of electrolytic solutions is due to cation as well as anion movement, the mobility of cation as well as mobility of the anions. So he found out that the limiting molar conductance lambda naught m, where naught indicates the limiting molar conductance of any electrolyte, let us say our electrolyte is x plus y minus. So x is a cation, y is an anion, is the sum of the limiting molar conductance of its cation plus limiting molar conductivity of its anion. This is called as KOHLRAUSCH law. Very important law, KOHLRAUSCH law. So what KOHLRAUSCH law says? It says that the limiting molar conductivity of an electrolyte is the sum of limiting molar conductivity of its cation and anion. That is called as KOHLRAUSCH law of independent migration of ions. So this KOHLRAUSCH law we are going to apply, we are going to solve so many problems. So what are the importance of KOHLRAUSCH law is, for example, if I take KOHLRAUSCH law using strong electrolyte, that is HCl is equal to limiting molar conductivity of H plus plus limiting molar conductivity of Cl minus. So for KCl you can write K plus plus Cl minus limiting molar conductance. Again a new word, limiting molar conductance is nothing but if you are calculating molar conductance of a solution at infinite dilution, highly diluted, nearly constant, where the concentration is become nearly zero. The concentration is nearly zero. At that infinite dilution, whatever the molar conductance is there, that molar conductance itself is called as limiting molar conductance. So very important application of limiting molar conductance, that is KOHLRAUSCH law, is that this KOHLRAUSCH law is used to calculate the limiting molar conductivity of weak electrolytes, because the weak electrolytes you cannot calculate the limiting molar conductance using experiments. Using experiments it's not possible to calculate the limiting molar conductivity of weak electrolyte. Why? Because the name itself says it's a weak electrolyte. Weak electrolyte means it will not get completely dissociated. For example, acetic acid, very famous example of weak electrolyte. It will not completely dissociate into acetate ion as well as H plus ion. The complete dissociation does not occur. completely it won't dissociate. Even at the infinite dilution, there will be, even at the infinite dilution, there will be some quantity of undissociated form will be there. Therefore you cannot calculate the, so it is not completely dissociated, incompletely dissociated form. Therefore it cannot be calculated by the experiment. So when it is not calculated by the experiment, we can calculate by using KOHLRAUSCH law. So using KOHLRAUSCH law, using our limiting molar conductancy of the strong electrolytes, you can calculate the limiting molar conductivity of the weak electrolytes. How? Let us consider. For example, if you want to calculate the limiting molar conductivity of acetic acid, limiting molar conductivity of the acetic acid, very important. So we can calculate by using limiting molar conductivity of acetate ion. This is what KOHLRAUSCH law says. It is the sum of the limiting molar conductance of its cation as well as anion, or individual contributions of cation and anion. So once you know the limiting molar conductivity of acetate ion as well as hydrogen H plus ion, then we can get the limiting molar conductivity of acetic acid. This is what our law says. So according to this law, we have to know that you can take any electrolyte which is containing this acetate ion, but it should be strong. Let us take acetate, a sodium acetate. This sodium acetate is a strong electrolyte. This limiting molar can be calculated by using experiment because it's completely dissociated, no? So you can get this limiting molar conductivity of strong electrolyte using experiment. So we got acetate ion here, we got acetate ion here, even though Na plus is there. Later on we'll see about that. Then we want one more H plus ion, so limiting molar conductivity of one more strong electrolyte you should take, which is containing H plus ion. I have taken, you have to observe, I have taken acetate ion containing one strong electrolyte, I have taken H plus ion containing another strong electrolyte. So these two, if you see, Na and Cl are extra. So this NaCl you need to subtract limiting molar conductivity of NaCl. This NaCl is a strong electrolyte. Strong electrolyte, strong electrolyte, strong electrolyte. That's all. So from the strong electrolytes, you can get the limiting molar conductivity of weak electrolytes. Just to use the formula. So just you need to derive the formula, that's all, because you need to take one ion, one strong electrolyte containing one ion, cation, and one strong electrolyte containing anion. So whatever the remaining extra ions are there, that strong electrolyte must be subtracted from that. So this is very important. So where we are calculating the limiting molar conductance of the weak electrolytes using KOHLRAUSCH law, which can be calculated directly from the experiment. So this is one application. Second application, you can calculate the degree of dissociation of weak electrolyte. Degree of dissociation, how much dissociation is happening, how much degree, to what degree the weak electrolyte is getting dissociated. Because I said it is not completely dissociated, it is incompletely dissociated. When it is incomplete dissociated, how much it is getting dissociated, that can be calculated by our KOHLRAUSCH law. That is, it says degree of dissociation alpha is equal to lambda m by lambda naught m. Once you know the molar conductance of that weak electrolyte, once you know the limiting molar conductance at infinite dilution, you can calculate its degree of dissociation just by lambda m by lambda naught m. Just you can get it. So you can also calculate the dissociation constant K of the weak electrolytes by using the formula C alpha square by 1 minus alpha. C alpha square by 1 minus alpha, where alpha is called as the degree of dissociation, which you have got in the above, just where C is the concentration. Using these equations you can calculate. So we need to remember these equations so that we need to solve the problems. So the first concept I will explain. So one is called as electrolytic solutions. So this concept you need to remember before going to solve the problems. So one is molar conductance as well as specific conductance as well as limiting molar conductance, and one more is KOHLRAUSCH law, in which these equations going to play a major role. These equations of KOHLRAUSCH law are going to play a major role, as well as you need to relate the weak electrolyte with the strong electrolytes. You need to derive your own equations. So we'll solve the problems there also, you can know. So these formulas you need to remember. Next part is you can see the next part is electrolytic cells. What is electrolytic cell? A cell, electrolytic cell is a cell which will use the electricity, which uses the electricity to perform a chemical reaction which is non-spontaneous. When the reaction is non-spontaneous, using this external source of electricity, we can make it occur, because non-spontaneous reaction which do not occur on its own, we are going to make it occur by using electricity, that is called as electrolytic cells. In these electrolytic cells, whenever you perform electrolysis using a cathode, anode and electrolytic solution, for example, let us take one of the best example of electrolytic cells. One is two copper are taken, copper as anode and copper as cathode. Two copper electrodes connected to electricity. So one is anode and one is cathode. So let us say our anode is a impure electrode and cathode is a pure electrode, pure copper and impure copper. So we have dipped in copper sulfate solution. So then when you apply to electricity, generally there is no reaction takes place between copper and copper sulfate. When you dip a copper in copper sulfate, there will not be any reaction which is going to take place. But when you apply electricity, the reactions start taking place. What the reactions occur is, at our anode, especially at this anode surface, our copper is converted to copper plus 2 by loss of 2 electrons. That means whatever the copper which is present in this anode will slowly dissolve in copper sulfate and it will form copper plus 2, losing 2 electrons. This copper plus 2 will move from one end to another end, that is, it is attracted towards cathode. At that cathode, this copper plus 2 will take up 2 electrons and it forms copper. So this is at anode oxidation, again at cathode reduction, as the method we have said, same in the electrochemical cells. So that copper, when it is dissolved in copper plus 2 from anode, will be deposited on the pure copper. So in this way we can get the pure copper from impure copper. If you take impure copper here and pure copper here, and they will also use for other metals also, to get pure metal from impure metal, these electrolytic reactions are taking place. See, the meaning is, copper is got deposited cathode, right? Exact or not? Our copper is got deposited cathode. So that means there may be deposition, there will be deposition of a material, of a chemical at one electrode, and there may be sometimes there may be liberation also takes place. There may be liberation and there may be deposition. For example, let us take NaCl solution, which is called as brine solution, right? Saturated NaCl solution is called as brine solution. That brine solution, let us take this brine solution, let us apply our platinum electrodes. See, generally you see, if you take salt solution and you have kept platinum into it, is there any reaction occurs? No, there is no reaction occurs, it's non-spontaneous. So but we are connected to electricity now. Chala, let's connect it to electricity. Once you have connected it to electricity, now the reaction starts happening. Our platinum did not react because our platinums are inert electrodes, they won't react with NaCl. But these NaCl, which is containing Na plus ions and Cl minus ions, Na plus will move towards the cathode and it will get reduced to sodium, and that forms sodium there. Whereas if you take Cl minus, it will lose the electrons and it will form chlorine gas. So this will happen at anode. So that means chlorine is a gas, will get liberated anode, whereas sodium is formed at cathode. Just you need to see that which is formed at anode, which is formed at cathode. It just depends upon oxidation and reduction. Cathode is reduction and anode is oxidation. This only you need to remember, and you need to see which is formed at anode and which is formed at cathode. So it is deposited, sodium will get deposited, chlorine will get liberated. So either deposition will occur or liberation will occur. So when electrolysis is going to take place, or electrolytic cells are going to take place. So this liberation or deposition, so the two laws have been discovered by scientist who is called as Michael Faraday. He has set two laws on this deposition or on that liberation, how much amount of substance is getting deposited or how much amount of substance which is getting liberated. So to calculate this, Faraday's has given two laws. So Faraday's first law says the mass of the electrode which has got deposited or liberated, you can say that the amount of chemical reaction which is happening, the chemical reaction may be deposition or the chemical reaction may be liberation. So the mass of the chemical which is got deposited or liberated at an electrode is directly proportional to amount of current which is passing through electrolytic solution. Amount of current, it is directly proportional to current. Here Faraday means current means charge, amount of charge which is passing through the electrolytic. How much charge is being passed, that charge will decide the amount of deposition or liberation. If more amount of charge, more deposition. If less amount of charge, less deposition. That's all. So it depends upon the amount of charge. We know charge is equal to current into time. How much amount of current which is passed into time is called as charge. So Q is equal to I into T, or I can write M is directly proportional to I into T. Or if you take out the proportionality constant, it will be M is equal to E into I into T, where E is called as electrochemical equivalent of that metal. Electrochemical equivalent of that material. E is equal to I in E is equal M is equal to E into I into T. Very important. So the most important thing. So one of the important thing is, so let's take up for example copper. To deposit copper plus 2 to deposited copper from copper sulfate, we know that our copper has Cu plus 2, it has to take up 2 electrons, correct? Let's take one more example. Silver, to deposit from silver chloride to form silver, that it has to take 1 electron. For example, one more, let us take chlorine, to get liberated as chlorine gas, it has to take 2 electrons, correct? Exact or not? So here how to apply this Faraday's first law. Faraday's first law says that the mass deposited electrode or the mass of our liberated of a component is directly proportional to the charge. See how many electrons are moving. The electrons are 2 electrons. 1 electron will always take 1 mole of electrons always take 96,500 coulombs of charge. 2 electrons means 2 Faradays of charge is required, correct? Because it's 2 electrons. 2 Faradays of charge is required to deposit copper. That means it's atomic mass of that copper. What is atomic mass of that copper? The atomic mass of that copper is 63.5 grams of copper. If you want to deposit, you need 2 Faradays of electricity or 2 into 96,500 coulombs of charge. Very important. Very, very important. This relating is important. Next, to deposit 1 atomic mass of our silver, atomic mass of silver has to get deposited means atomic mass of silver is 108. That means 108 grams of silver to get deposited. We require how many Faradays? Only 1 Faraday of electricity is required. Depends upon the number of electrons that are required. So this number of electrons must be kept in mind. Those many Faradays are required to deposit this many. If you take in chlorine, how many number of Faradays are required? 2 electrons. Therefore 2 Faradays are required to deposit. See, it is forming, not forming an atom, it is forming molecule, right? So you should take molecular formula. 35.5 is the atomic mass of chlorine. So if you take molecule is being formed, molecular formula. So molecular formula is 71 grams of chlorine to get liberated means we need 2 Faradays. So that means 2 into 96,500 coulombs of charge is required. So this clarity is most important in solving the problems. The number of electrons that are being involved for deposition or liberation, those many Faradays of electricity is required to deposit that much atomic mass of an element or those many atomic mass. If it is molecular mass of that compound should be required for its that is liberated, right? So this is called as Faraday's first law. Very important, hope you understood. So we'll apply this in the problems. That's the reason why I'm taking it too clearly. So second one, Faraday's second law of electrolysis. Faraday's second law of electrolysis says that whenever you pass same amount of current through two electrolysis of two solutions. For example, if it is happening copper sulfate solution is electrolyzed here using copper electrodes. If it is silver chloride is being electrolyzed using silver electrodes, let us say. So copper sulfate as well as silver chloride, but we are passing same amount of current. Current is same, here also Q amount of current, here also Q amount of current. Then the question is, how much amount of copper is getting deposited, how much amount of silver? Is it same current means same amount of deposition will occur? No. So the amount of mass of deposition or liberation when same amount of current is passed through the electrolytic solution is depend upon its electrochemical equivalence. M1 by M2 is equal to E1 by E2. That is, mass of deposition of first component depends upon its electrochemical equivalent. Mass of second component depends upon its electrochemical equivalent. That is, electrochemical equivalent is nothing but its atomic weight by atomic mass or atomic weight by the number of electrons that are happening to reduce or number of electrons that are taken part to oxidize. See this number 2. If it is copper, atomic mass by 2. If it is silver, atomic mass by 1. If it is chlorine, atomic mass by 2. Like that is take atomic mass by number of electrons that are required for reduction or number of electrons that are required for oxidation. So when the condition is there should be same amount of current that should be passed to the electrolytic solution, same amount of current should pass. So hope you understood. So let's solve the problems. So these all concepts should be very clear when you are solving the problems. First question. A solution of nickel nitrate is electrolyzed between two platinum electrodes using 0.1 Faraday electricity. How many moles of nickel is being deposited? A solution of nickel nitrate is being electrolyzed. See, he has asked how many amount is deposited. So deposition, liberation is Faraday's law. So our given nickel nitrate is given. So this nickel nitrate consisting of nickel as nickel plus 2, nitrate as NO3 minus. Exact. So what is being deposited is a nickel is being deposited. So when nickel has to deposit from nickel plus 2, so it has to take how many electrons? It has to take 2 electrons, right? So our question, so let's go for the question now. 0.1 Faraday of electricity is passed. How many moles of nickel is being deposited? So how many moles are being deposited means, so we know that according to Faraday's first law, when there are 2 electrons are involved, 2 moles of electrons are involved forms 1 mole of nickel, right? It is forming 1 mole of nickel because he is asking in terms of moles, we are taking moles. If he is asking in terms of grams, we would have taken atomic mass of the nickel like this here, right? So 2 moles of electrons means how many Faradays? 2 Faradays. 1 mole will have 1 Faraday, 2 moles means 2 Faradays. So 2 Faradays electrons are forming, 2 Faradays of charge is forming 1 mole of nickel. What's our question is, according to question, 0.1 Faraday will form how many moles of deposition? So let us take it as how much? X. Just crisscross cross multiply and you will get the answer. Cross multiply 2 into x, cross multiply 2x is equal to 1 into 0.1 is 0.1. So x is 0.1 by 2, that's nothing but 0.05. So answer is 0.05. Very clear, very easy. So just you need to write this reaction of deposition or liberation, whatever it is given. Then you need to relate with the number of electrons and number of moles. If it is asked in the question moles, you need to take up mole. If it is asked in the question, if it is grams, you should take atomic mass. Then simply crisscross and get the answers. Second question. Lambda naught m, limiting molar conductivity of NaCl, HCl and NaAC. Here it is. So maybe some mistake might have came. NaAC. Actually it should be NaAC, maybe typing mistake. So that is sodium acetate, R126.4 for 25.9 and 100.5 Siemens centimeter square per mole respectively. The conductivity of 0.01 molar acetic acid, this is the acetic acid, HAC should be given, again C is most. So acetic acid is 5 into 10 to the power of minus 5 Siemens centimeter. Degree of dissociation is of acetic acid, acetic acid is. So the question is very clear. Limiting molar concentrations are given, and is given the conductivity. The conductivity means, what is conductivity means? Specific conductance, I said. So specific conductance of concentration is also given. So what is the degree of dissociation is being asked. So the given terms, let's write, very easy. Just you need to write the given terms and you need to substitute in the formula. So limiting molar conductivity of NaCl is given. NaCl is given as 126.4. Again limiting molar conductivity of HCl is also given. HCl is 425.9. Again limiting molar conductivity of NaAC, that means sodium acetate, is given 100.5 Siemens centimeter square per mole. So if the conductivity of HCl, that is conductivity means G, conductivity is given, specific conductance is given for that is our CH3COOH, which is called acetic acid. So it is being given as 0 is 5 into much it is 5 into 10 to the power of minus 5. So this specific conductance, conductivity or specific conductance is also given. Concentration is given as 0.001 molar, and degree of dissociation is being asked. Degree of dissociation, alpha is equal to question mark. We know alpha is nothing but lambda m by lambda naught m. According to our KOHLRAUSCH law, you studied this, that lambda is equal to alpha m. Alpha is equal to lambda m by lambda naught m. What is lambda m? Lambda is nothing but molar conductivity. Molar conductivity. Molar conductivity is nothing but 1000 into kappa by C. Do you remember this? Because this is kappa. Specific conductance, right? Conductance is called as K. Specific conductance or conductance is called as kappa, 1000 into kappa by C. So from this you can get lambda m. So next, how to get lambda naught m? Lambda naught m of the acetic acid cannot be calculated directly. So you should calculate it from using the limiting molar conductivity of strong electrolytes, right? So 1000 into, what is kappa? Kappa is given as 5 into 10 to the power of minus 5 by, what is C? Concentration is given as 0.001. So when you calculate this, you will get answer, that is equal to, so let's take out, that is 1000 into 5 into 10 to the power of minus 5. 0.001 means 10 to the power of minus 3. If it is taken to numerator, you get 10 to the power of 3. So 10 to the power of 3 means, so 10 to the power of minus 5, 10 to the power of 3 will become 10 to the minus 2. 10 to the power of minus 2, here 2 zeros will get cancelled, so nearly we will get 50, right? Exactly 50. Lambda naught, you got lambda naught is 50. Then we need to calculate lambda naught m and just substitute, we will get the exact answer. So to get the lambda naught m, that is limiting molar conductivity of weak electrolyte acetic acid. Limiting molar conductivity of acetic acid is CH3COOH is equal to limiting molar conductivity of CH3COO minus plus limiting molar conductivity of H plus. This is what Kohlrausch law says. The limiting molar weak electrolyte is any electrolyte is sum of the limiting molar conductivity of cation and anion. So how to get it from cation? So for that cation you need to take one of the strong electrolyte. For anion I have taken one strong electrolyte containing anion, another strong electrolyte containing anion, minus whatever the extra we didn't require. So Na and Cl we didn't require, minus NaCl, right? So just substitute. We got sodium acetate is given 100.5, so it is given as 100.5, plus HCl is also given, limiting molar conductivity is 425.9, minus NaCl is given 126.4. so when you subtract all these you will get 400 Siemens centimeter square per mole. So just we need alpha, right? So just we need to substitute here. That is alpha is equal lambda naught m, we got 50 by lambda naught m is we got 400, lambda m is 50, lambda 50 by 400, which is equal to 0.125. so our answer is 0.125. so very easy question actually, but what he has done is two concepts he has mixed up. He has mixed up a concept of limiting molar conductivity of Kohlrausch law, that is being given limiting molar conductivity of weak strong electrolytes. He asked for weak electrolyte. Then he has given the kappa, that is specific conductance, and you need to calculate lambda. So then he has asked for degree of dissociation, that is lambda m by lambda naught. First lambda